Welcome to this explainer. I am your host, the strategist, and today we are putting on our lab coats and stepping straight into the diagnostic clinic. Our patient today, the Cambridge 0625 Physics syllabus. If you've been feeling entirely overwhelmed by the epic journey of how thermal energy and waves operates, you are in the exact right place. Today, we are diagnosing the symptoms of a failing answer and prescribing the ultimate cure. Now, in our clinic today, we have two typical students we are going to learn from. First, there's Alex. Alex is brilliant but overloads every single answer with raw physics facts and absolutely no analysis. Then we have Sam. Sam rushes, completely misses the command word requirements, and leaks marks all over the exam paper. We are going to look at their flawed answers, break this down, structure it visually, and most importantly, make it stick so you don't make the same mistakes.
But first, I really want to hook your attention with a symptom of a very, very common misunderstanding. Let's diagnose this together. If the space between the sun and the earth is an absolute vacuum, just pure empty nothingness, how does the sun actually warm our planet? Think about it for a second. Alex might write a whole paragraph about hot gases, while Sam might just guess gravity. But conduction needs solids, right? And convection needs fluids. So how does that thermal energy travel 150 million kilometers through an absolute void to reach us? Keep that in your mind, because diagnosing that correctly is exactly how you start securing those top-tier marks.
All right, here is our syllabus roadmap, our diagnostic checklist for today. First, we'll cover thermal radiation basics. Then, we move into specific heat capacity. Third, we'll break down the mechanics of waves. Fourth, the characteristics of sound. And we'll wrap it all up with a comprehensive revision summary. Let's not waste any time. Let's dive right into Section 1, Thermal Radiation Basics. Okay, to answer our earlier question about the vacuum of space, the sun's energy actually travels to us as electromagnetic waves, specifically invisible infrared waves, which can easily travel through a complete vacuum. When they finally hit an object, like the Earth or you standing in the sun, they are absorbed and they heat that object up. But here is the absolutely crucial point that examiners want to see you explain using the Peel framework: point, evidence, explanation, link. Not all surfaces treat these infrared waves the same way. We divide surfaces into two camps. On one side, we have good emitters and good absorbers. These are your matte black, non-shiny surfaces. On the other side, we have poor emitters and poor absorbers, which are white, silvery, and highly reflective. This isn't just theory. It's why houses in hot, sun-baked countries are so often painted white. It's to reflect that thermal radiation and keep the inside perfectly cool. Alex would just say white is cold, but you need to explain the reflection of infrared radiation to get the mark. Notice the visual spectrum we're looking at here. Matte black sits firmly on the absolute best side for both absorbing and emitting, while silver sits entirely on the worst side for absorption and emission, but makes for a truly fantastic reflector. If you want a saucepan to cool down quickly, black is your best bet, because it emits that energy at a much faster rate than a white or silver one. Before we continue, subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's keep building our strategy. When you see a question about cooling rates, immediately think of this spectrum. Now, examiners absolutely love to test your knowledge of this using two classic experimental setups. Look closely at these. On the left, to compare emitters, we use a metal Leslie cube filled with boiling water, so all sides are at the exact same temperature. A detector measures which side radiates the most energy. On the right, to compare absorbers, a radiant heater sits squarely between a matte black plate and a white plate. Thermometers attached to the plates reveal which one heats up the fastest when exposed to the exact same amount of radiation. When Sam sees this in an exam, Sam rushes and mixes up which experiment is for emission and which is for absorption. Don't be like Sam. Take a breath, read the command word, and identify the setup. Moving on to our next diagnosis, Section 2, Specific Heat Capacity. So we know how energy travels via radiation, but what exactly happens when a material actually absorbs it? Well, its internal energy increases. Let's diagnose the formula for this step by step to prevent any cognitive overload. The energy transferred to an object to increase its temperature relies on four key variables. You have E, the energy transferred, measured in joules. This equals M, the mass in kilograms, multiplied by C, the specific heat capacity. And specific heat capacity is simply how much energy is needed to raise 1 kilogram of that specific material by 1 degree Celsius. Finally, you multiply by the change in temperature, or delta theta. E equals mc delta theta. Memorize that. And here's where Sam drops two whole letter grades. Sam forgets to convert grams to kilograms before plugging the numbers in. always check your units. To really cement this concept, let's look at a direct visual comparison. We have exactly 1 kilogram of water and 1 kilogram of aluminum. To raise the water's temperature by just 1 degree Celsius, it demands a massive 4,200 joules of energy. But the aluminum, it only needs 900 joules to achieve that exact same 1 degree rise. This tells us that different materials require vastly different amounts of energy to change temperature. Water is uniquely stubborn when it comes to heating up, which is why it's used as a coolant in car engines. It can absorb a massive amount of thermal energy without its own temperature spiking out of control. That is a brilliant real-world application you can use to bulk up your explanation marks. So how do we actually find out that water takes 4,200 joules? We do it through practical experiments like the setup you see right here. We place an electric heater into an insulated beaker of water. We know the power of the heater in watts, and we time how long it switched on in seconds. Because energy equals power multiplied by time, we can calculate exactly how many joules were transferred to the water. Then, we measure the temperature rise with a thermometer and easily rearrange our E equals mc delta theta formula to calculate the specific heat capacity. It is a beautiful, logical progression if you just follow the math.
Let's shift our focus to Section 3, the mechanics of waves.
Stop scrolling. Subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to AC Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, shifting gears from stored internal energy, let's look at how energy moves through different mediums. To master waves, you need a highly precise diagnostic vocabulary. First up is wavelength. This is simply the distance between any point on a wave and the exact equivalent point on the next wave. For example, the distance from one peak directly to the very next peak. Get this definition perfect, because close enough is not good enough for Cambridge examiners.
Next is amplitude. Imagine the water in a pond when it's perfectly still and flat. That is the rest position. The amplitude is the maximum distance the water is displaced from that flat rest position when a wave actually passes through. It is essentially the height of the wave peak from the center line. Here's a quick challenge for you. If Alex writes amplitude is from the bottom of the wave to the top of the wave, what is the flaw? The flaw is that Alex just described double the amplitude. It must be from the rest position to the peak. Do not fall for that trap.
Then we have frequency. This is the sheer number of oscillations or complete waves that pass a single point every single second. It is measured in hertz. And here is a crucial exam tip that links these concepts together. The period of a wave, which is the total time it takes for just one complete wave to pass, is simply 1 divided by the frequency. If you see an exam question asking for the period and they've only given you the hertz, just divide 1 by that number and you have got your answer. It is free marks if you know the rule.
Let's anchor this visually. Look at these wavefronts spreading out from a speaker. Those dark blue bands are areas where the air is actively compressed. The distance between one dark band and the exact next dark band is your wavelength. As these wavefronts travel outward, the number of them that hit your ear every single second is the frequency. Alex would look at this and just write sound is moving. But you are going to use specific terms like compressions, wavefronts, and frequency to guarantee you get the maximum allowable marks.
Now, these variables aren't just isolated definitions floating in space. They are permanently linked by an absolute must-know calculation, the wave equation. The speed of the wave, v, measured in meters per second, is equal to the frequency f in hertz multiplied by the wavelength represented by that lovely Greek letter lambda. If you know any two of these, you can always diagnose the third. I want you to do a speed writing challenge right now. You have 30 seconds in your mind to write one perfect Peel paragraph explaining how, if the frequency of a wave doubles, but the speed stays the same, what happens to the wavelength? It halves. Boom! That's analytical thinking.
Let's apply this directly in Section 4, Characteristics of Sound.
Applying our wave mechanics to what we experience every single day. Sound waves are longitudinal waves. This means they travel as a series of compressions, where particles are squashed together, and rarefactions, where particles are stretched apart. Now it's time to clarify a massive exam trap that catches out thousands of students every year. Students often mix up pitch and volume. They are entirely different mechanical properties. The pitch of a sound, whether it is a high squeaky whistle or a low booming bass note, is dictated purely by the wave's frequency. The volume, or the sheer loudness of the sound, is dictated entirely by the wave's amplitude. Keep them separate in your head.
Looking at an oscilloscope readout makes this absolutely visually apparent. On the left, we see a much tighter, more frequent waveform. Because more waves are packed into the exact same space, it has a higher frequency, which directly translates to a higher pitched sound than the more stretched out wave on the right. Notice something else? Their amplitudes, their heights from that center rest line, are roughly the exact same. This means they are equally loud, just completely different pitches. If you can read an oscilloscope like this, you are thinking like an examiner.
And as sound waves, or any waves for that matter, like the ones you see in a ripple tank experiment, travel, they exhibit 3 core behaviors you absolutely must be able to identify. Reflection is when waves bounce back, which is exactly what causes echoes in an empty room. Refraction occurs when waves actually bend because they change speed, like water waves moving from deep into shallower water. And finally, diffraction, which is when waves bend or spread out as they pass around an obstacle's edge or push through a gap. Memorize these 3 behaviors.
Finally, let's pull all of this together in Section 5, Revision Summary.
Let's wrap up our diagnostic session with a final health check. I want you to take a mental screenshot of this exact revision checklist, derived straight from the source syllabus. Here is the complete physics answering system, the 3 rules that guarantee top marks. Rule 1, command word decoding. Don't be like Sam, read what the question is actually asking. Rule 2, Peel framework application. Make your point, back it up, explain it, and link it back. Rule 3, time management matrix. Don't spend 10 minutes on a 2-mark question like Alex. If you are doing the core paper, ensure you've nailed down the meanings of amplitude, frequency, and wavelength, and you can utilize that wave equation effortlessly. If you are aiming for the extended level, you need to go deeper into compressions, rarefactions, and linking temperature directly to kinetic energy. Listen to me, students. Who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. So my final provocative question for you today. You now know the underlying physics of how thermal energy travels across the sheer vacuum of space, how it is stubbornly stored in water, and the exact mechanics of the wave equation, but knowledge is only potential power. How will you apply these visual, structural lessons directly into your next past paper practice? The tools are now in your hands. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.